Welcome back. In this lesson, we'll switch our focus from a conceptual look at density to a quantitative one. NASA has developed a new alternative rocket propellant that is safer, higher performing, and less costly. It's also denser than prior options, which means in the same volume, more mass can be stored for use. Let's say we have a question like this one, where we need to calculate the density of NASA's new fuel. This type of question represents the first of two general types of density calculations we'll do. This type of problem deals with finding the density if given a mass and a volume. That is the focus of this lesson. The second general type of problem will be covered in the next lesson. As we saw in density part 1, density equals mass over volume. So to solve this, we'd first write our formula. Then before we plug in for mass and volume, make sure the units match what we need to solve for. We see here the requested units are grams per centimeters cubed. Well, the mass we're given is in grams and the volume is in centimeters cubed, so we're all set.
Remember to take care of your units. Don't just plug into a formula without thinking about what the units are.
We now plug in and then solve to get 1.46 grams per centimeters cubed. Notice this density of 1.46 is almost 50% greater than the traditional rocket propellant hydrazine, which is only 1.01. Let's do another one where we need to find the density. Now, unlike the previous problem, this time we don't have the units we need at the end. We want grams per milliliter. We do have milliliters here, but we don't have grams yet. We have pounds. So step 1 is to first convert pounds to grams. For this, we'll use conversion factors. We start by identifying where we want to end up. In this case, that's grams. Then we write down what we start with, 4 pounds. Now we start our first conversion factor with pounds on the bottom because we want to cancel it. Don't put any numbers in yet though. A number wouldn't make sense until we know what unit goes in the numerator. Now the question is, what unit does go in the numerator? Well, it must be grams, right? After all, we need to solve for grams. Well, it would be fine to put grams in the numerator if you knew how many grams are in a pound. We don't. At least it's not provided. But we do know how many kilograms are in a pound. So let's try converting to kilograms. And since we're told there are 0.454 kilograms in 1 pound, we had 0.454 by the kilograms. Okay, now I'd like you to stop the video and finish this problem on your own. Here are some hints. First, to finish step 1, you need to add one more conversion factor and then solve for grams. Second, as a separate calculation, you need to solve for density. Stop the video now. For the next conversion factor, we put kilograms in the denominator to cancel it and grams in the numerator, because that's what we need to solve for. We put 10 to the third in the numerator because we need to remember there are 10 to the third grams in a kilogram. If you put 1,000 instead of 10 to the third, that's fine too. We then do the math and get 1,816 grams. Now as a separate calculation, use the density formula to solve for density. We plug in our values and eventually get 3.5 grams per milliliters. We've rounded to two significant figures because the numerator here is really considered to be 2 sig figs because of the 2 sig figs way back here. This last one is a problem we might encounter in the laboratory. If you have an object that is insoluble in, unreactive with, and more dense than water, you can find its volume by the water displacement technique. That is, the graduated cylinder on the left represents the level of water in a graduated cylinder before adding the object, and the graduated cylinder on the right represents the new level after the object has been added. So step 1 is to find the volume of the solid object. It will be the same as the amount of water displaced. We need to read the volume in a graduated cylinder from the bottom of the meniscus, i.e. the bottom of the curve. In both cases, that would be where the dashed red lines now are. And keeping in mind we measure values to one uncertain digit, the before picture looks like the bottom of the meniscus is about 28.8. We can't be sure it's 0.8, might be 0.7, might be 0.9. The point is it's okay to estimate that last digit. So the initial volume is about 28.8 milliliters. In the after diagram, it appears the bottom of the meniscus is right on the 37 milliliter mark. Therefore, we would call that 37.0, not just 37. So to find the volume of the object that was placed in the water, we subtract final minus initial to get 8.2 milliliters. Since milliliters and centimeters cubed are identical, that also means we have a volume of 8.2 centimeters cubed. Now that we have the volume squared away, and we already have the mass, 30.5 grams, we can now do a second step and plug into the density formula and get our answer. Well, that's it for density part 2. where we did calculations to find the density. In Density Part 3, we'll complete the trilogy by doing calculations to find mass or volume if given the density. Thanks for listening, and see you next time.